Good day, students. Welcome to mathgotserved.com, where we don't just solve, we teach. In this clip, we're going to be going over problems 11 to 15 of the June 2019 Algebra 1 New York Regents exam. We're going to be having a detailed consideration of how to solve the problems. If you want a much quicker coverage, do visit our website so that you can gain access to the solutions to the problems. Don't forget to subscribe to our channel so you can get updates to the remainder of this review series. Alright, let's take a look at question number 11. In question 11, we're going to be focusing on how to identify linear versus exponential functions. As you can see, the options are provided to us in word form, so we have to translate the verbal representation into algebraic representation in order to determine if it's a linear function or an exponential function. Question 11 reads, which situation can be modeled by a linear function? Alright, before we get started with the identification of which of these represent a linear function, let's do a real quick review on what a linear function is. So how would you describe a linear function? Something you want to note is as follows. Linear functions grow by adding a constant. We can call the constant, let's say m, okay? By adding a constant m repeatedly. So think about linear functions as a growth by repeated addition, okay? If you're adding the same number over and over again, the terms that are generated by that process is going to be the output values of a linear function. Alright, and then the formula for linear functions is basically y equals mx plus b. This is the slope-intercept form of a linear equation. Alright, m represents that value you keep adding, and b represents the original amount. Okay, alright, so let's go ahead and take a look at these options right here to see which one is a linear function. And then just a side point, exponential functions, just to help you see the difference, exponential functions, what do you think happened with exponential functions? They grow by repeated multiplication. Okay, so if you generate terms of a function by multiplying, then it's going to be an exponential function, repeated multiplication. And then you can think about an exponential function as y equals a times b to the x. Okay, alright, so b in this case represents your growth or decay factor. What do you multiply by over and over again, or what do you divide by over and over again? That's what b is. Alright, okay, so the first one says the population of bacteria triples every day. So triple represents what kind of operation? To triple means you multiply by 3. Okay, so how do the terms of this function grow? They grow by multiplying by 3 every time. So you multiply by 3 repeatedly. So if you're multiplying by 3 repeatedly, what kind of function is that going to be? It's clearly exponential, so this is not what we're looking for. We're looking for a function that's linear. Okay, so an example of option 1 will be y equals, let's say, 5 times 3 to the x. So this just indicates repeated multiplication by 3, because when you multiply by the same number repeatedly, the condensed form is an exponential function. Alrighty, okay, question 2, option 2, the value of a cell phone depreciates at a rate of 3.5% each year. So rate of, what operation do you associate with of? Of represents multiplication. Okay, so the rate is being multiplied by a depreciation factor of 3.5% each year. Alright, so the rate is decreasing by 3.5% each year. What's going to be happening is we're going to be multiplying by 100% minus 3.5%. That's what we're going to be multiplying by. Okay, so depreciating by a rate of 3.5% basically means that you multiply by 1 minus 1 represents 100. 3.5% in decimal form is 0.035. Okay, so you multiply by 1 minus 1.035 repeatedly over and over again, and that's what will generate the terms of this depreciating function. Okay, so what kind of function is this? If you're multiplying by 1 minus 0.035 over and over again, is that linear or exponential? Since it's repeated multiplication, this is an exponential function, so this is not what we're looking for. Okay, all right, so let's take a look at an example of option 2. Okay, so what kind of function could represent option 2? So let's say your cell phone is $100. No, that's kind of cheap. Let's say it's $1,000. Okay, like the new Note, cell phones from Samsung. Let's say it's $100 and it depreciates by this, $1,000 and it depreciates by 3.5% every year. If we want to model that algebraically, it's going to look something like y equals 1,000 times 1 minus 0.035 raised to the x power. You can see this representation right here is that of an exponential function. Okay, all right, so don't forget, if you have rate of a certain percent, is basically repeated multiplication. Depreciation indicates subtraction, and if it were appreciation, we will add this percentage value to 1. Alrighty, okay, now let's take a look at option 3. An amusement park allows 50 people to enter every 30 minutes. So what do you think is happening here for this particular one? 50 people enter the park every 30 minutes. So that entry, what operation is it when people are entering the park? This operation right here indicates addition. Okay, so when you're adding, let's say you're adding $50 to your bank account every 30 minutes. I mean, if $50 is entering into your account every 30 minutes, it means addition, right? Okay, so in this case, what we're looking at is you add 50 repeatedly. All right, add 50 repeatedly, ladies and gentlemen. This is basically what a linear function is, repeated addition. So the answer to question number 11 is option 3. Okay, so let me show you an example of what that looks like if you want to add 50 every single time. An example function is y equals 50x. Okay, so this is a representation of a linear function where 50 is added at every input value x. Alright, so we know what the answer is, but let's just take a look at option 4 and see what's going on in that scenario. For option 4, it says a baseball tournament eliminates half of the teams after each round. So there goes that off again, and half. So half of, what does that tell you? Multiplying by 1/2, as we saw in option 2. So whenever you see that off component and a particular factor, it will tell you that it's a repeated multiplication, and this, ladies and gentlemen, is an exponential function, and that's not the answer that we desire. Alrighty, so in option 4, what's happening is that we are going to be multiplying by 1/2 every single time. Okay, so option 1 is exponential, 2 is exponential, 3 is linear, and 4 is exponential. So let's take a look at an example of what option 4 looks like. So let's say there were 100 team members to start. Okay, so it's going to be y equals the initial amount 100 times the decay factor, which is 1/2, raised to the x power. And as you can see, this is a representation of an exponential function. That's why it doesn't fit the description. All right, so the question to number 11. The answer to number 11 is option number 3. Alright, let's take a look at question 12. In question 12, we are being assessed on how to calculate the percentage of a whole. Okay? Question 12 reads, Jenna took a survey of her senior class to see whether they preferred pizzas or burgers. The results are summarized in the table below. Okay, so we have the table right here. We have the rows are represented by the gender, male or female, and then the columns represents the food type. They prefer pizza or burgers. Question, of the people who preferred burgers, approximately what percentage were female? Okay, alright, so before we get started with this problem, let's go over what the formula for calculating the percentage of a whole is. Alright, so formula for percentage of whole. Okay, so the percentage of a whole is given by the formula part divided by whole multiplied by 100. Okay, so this 100 component basically converts it to percent. Alright, so what's the situation here? What's the whole and what's the part? Let's go ahead and identify what those components are so we can solve the problem. So we're looking for the percentage of female who preferred burgers. So which one is the part and which one is the whole? If you look at burgers as a whole, those who preferred burgers are composed of two genders. Okay, it's either male or female. So the whole is basically the total number of people that preferred burgers. Alrighty, so let's go ahead and write that down. The whole component of the formula is the total number of people. Total number of people, I'm going to write it as PPL, okay? Total number of people that prefer burgers. Okay, so this is a combined value, so it's going to be 42 for male plus 26 for female, giving us a total of 68. So that's our whole. Alrighty. Now, what's the parts? We're looking for the percentage that were female. So this piece right here, the female numerical figure represents the part. Okay, so 26 out of the whole represents a fraction of females that preferred burgers. So let's indicate what our part is. In this problem, the part is given by the number of females that preferred burgers. Okay, so what is that value? It's 26. Alright, so this is our part, and 68 is basically our whole. Alright, so it looks like we have everything that we need to solve our problem. We just need one unknown, so our unknown is the whole, percentage of whole. Okay, so let's write down our statement. The percentage of women, or say women or females, percentage of females, not women, percentage of females who prefer burgers. Now using the formula is going to be part, which is 26, divided by whole, was whole 68, multiplied by 100, and that should give us our desired result. Okay, so let's go ahead and fire up our calculators. Alright, we're going to compute this. So it's going to be 26 divided by 68 multiplied by 100. So it's 38.2352, so we're rounding it to one decimal place, so it's going to be approximately 38.2%. This 38.2% represents the percentage of females who preferred burgers. Okay, answer to question 12 is option number 2, and this is how you calculate the percentage of a whole given a tabular representation. Alright, let's take a look at question number 13. In question 13, we're going to be looking at how to solve inequalities into variables. Question 13 reads, when 3a plus 7b greater than 2a minus 8b is solved for a, the result is... So what we have here is an inequality. Okay, so what are we supposed to do when we're asked to solve for a particular variable in an inequality? So let's write down something to keep in mind. What it means to solve. To solve an inequality or equation, for a variable means what? It means to isolate. Okay, you want to get that variable by itself. Isolate that variable using the properties of equality. Using properties of equality or inequality, depending on what you're working on. Alrighty, in this particular case we're going to be using the properties of inequality because it's an inequality that we have. So the task is to solve for a. So just look at the word solve as isolate. Alright, so we have an inequality 3a plus 7b is greater than 2a minus 8b. So the goal is to get the a by itself. Okay, so what we are going to do first is collect like terms to different sides of the equation. We want all the terms with an a component on the left side and every other term without a's on the other side of the inequality. Alright, so what we're going to do is we're going to move the terms with the b's to the right side. So on the left side we have positive 7b. Okay, so we need this term on the right side. So how do we move positive 7b to the right side of the inequality? We use the inverse operation, right? So plus 7b, the inverse is minus 7b. So what we're going to do is subtract 7b from both sides of the inequality. Alright? So this property is similar to that of equations 2, of equality 2. So what happens? We have 3a. Now, positive 7b minus 7b, those two add up to 0, so that's gone. 3a is greater than 2a. Now, what is negative 8b minus 7b? The signs are the same. Okay, so when you're combining terms with the same sign, what do? You add and keep the sign. Preserve the negativity and add the coefficients. 8 plus 7 is 15, so it's 15b. Bam. Okay, we're looking better now because we have only a on the left side, but we have a problem. We have a term with an a on the right. So we need to move this term to the left side of the equation. Okay, so this 2a has a sign. It's a positive. Okay, if a term doesn't have a sign, the default sign is positive. So our goal now is to move this 2a term to the left side of the equation. What is the inverse of plus 2a? The inverse of plus 2a is minus 2a. So we're going to subtract 2a from both sides of the equation. And let's see what that yields. Now on the left side, what is 3a minus 2a? Signs are different, so we're going to subtract. Okay, subtract and keep the sign of the bigger term. The bigger term is 3a positive, so we'll keep that sign. 3 is bigger than 2, so we'll keep the sign of the positive. 3 minus 2 is 1, so we're going to be left with just 1a. If the coefficient is 1, you don't have to write it. Okay, so there's like a 1 here, but you don't write it. 1 is like the invisible coefficient. Alright, so 3a minus 2a is a, and that's greater than 2a, positive 2a minus 2a are inverses, they add up to 0, so we're left with negative 15b. Alright, so our answer is a is greater than negative 15b. How do we know that we're done solving? We know that we're done solving because a has been what? A has been isolated. Isolation of a variable is basically what solving that inequality or equation for that variable means. Alrighty, so the answer to question number 13 is option number 4. Alright, let's take a look at question number 14. In question number 14, we're going to be assessing how to find three things, basically how to find zeros, intercepts, maximum and minimum of linear and or quadratic functions. Question 14 reads, three functions are shown below. So we have three functions here, a, b, c. A is a linear function in an algebraic form. B is a quadratic function in factored form or zeros form. And then option C is another quadratic formula, quadratic function presented in graphical form. Okay? Alright, so the question is as follows. Which statement is true? So we have four statements here, and the question is which of them is true based on the functions that we have to the left. Alright, so we're just going to walk through all four of them step by step and then see which one generates the answer that we desire. Okay, so we're looking for a situation where both scenarios hold true. Now, the first one, option 1, it says B and C have the same zeros. So we're looking at B and C, our quadratic functions here, and then it says both of them have the same zeros. So let's start with option B. We want to find the zeros of function B, okay? Zeros of B. How do you find the zeros of a quadratic function? To find the zeros of a quadratic function in algebraic form, what you do is you set that function equal to 0 and solve. Alrighty? So that's what we're going to do right now. So to find the zeros for option B, we're going to set that function, which is x plus 2 times x plus 6. We're going to set it to 0 and solve. The nice thing about this is that it is nicely factored for us. So we're going to use the zero product property, the ZPP, to solve this. You take the first factor, x plus 2, set it equal to 0, and the second factor, set it to 0. That is what the zero product property is. Okay? Now let's solve them independently. We have two equations here. From the first one, we subtract 2 from both sides of the equation to get rid of this plus 2 and have x isolated. In the second equation, we're going to subtract 6 from both sides of the equation. Minus 6 is the inverse of positive 6. That will result in the isolation of x, and that will tell us what the second zero is. So for the first one, when we subtract 2 from both sides, that adds up to 0. We have x equals negative 2. That's our first zero. And the second zero for function b, f of x, plus 6 minus 6 is 0. X equals negative 6. Alright? So our zeros are negative 2 and negative 6. Let's write it down. So zeros are, in set roster notation, negative 6 and negative 2. Okay, so for option 1, B and C have the same zero. So now let's move on to the situation with C. What are the zeros of function C? If you take a look at the graph provided, which is a graph of function C, we have a quadratic presented in graphical form. So how do we find the zeros of a quadratic in graphical form? To find the zeros of a quadratic in graphical form, all you are looking for are the x-intercepts. Okay? So if we can find out what the x-intercepts are here, then we will know what the zeros of function C are. Okay, so what are x-intercepts? X-intercepts are the points where the graph intersects the x-axis. Okay, so this is your x-axis, so this is your first x-intercept, and that's your second x-intercept. So this value, we have 1, 2, -2, and then -3, -4. Alrighty, so this is your, these two are called your x-intercepts. So this x-intercept is -4, and then this x-intercept right here is -2. So guess what? Your x-intercepts are exactly the same thing as your zeros. Alright, it's called zeros because at that particular point h of x has a 0 value. Alrighty, so to find the zeros of function c or h of x, we're just going to write down the x-intercepts, which are x equals -2 and x equals -4. So for function c, the zeros are, what are the zeros? -4 and -2. So the question is, do b and c have the same zeros? Do they? The answer is no. One of your zeros are the same, which is -2, but -4 and -6 are different. So they do not have the same zeros. Both of them have to be exactly the same in order for them to have the same zeros. Okay, so conclusion, b and c do not have the same zero. Okay, b and c do not have the same zeros. So what does that tell us? It tells us that option number 1 is not true. Okay? Alright, so we're going to move on to option 2. Option 2, a and b have the same y-intercept. Alright, so let's do that one. Well, to find, how do we find y-intercepts of functions? Well, to get the y-intercept, it's not that complicated at all. To get the y-intercept basically means you set your x to 0. Alright, that's universal. It doesn't matter if you have a linear function or a quadratic function. Okay, so for option 2, we're going to look for the y-intercepts of both of them. Alright, so for y-intercept of function a, guess what we're going to do? We're simply going to evaluate that function when x, the independent variable, is 0. Okay, so we're going to look for that. Okay, so let me take that up. So for the y-intercept of a, option a is g of x, we're just going to set the x to 0. So for a, we have the function g of x equals -3 over 2x plus 4. So to find the y-intercept, guess what? We're just going to plug in 0 for x. So g of 0 is going to be -3 over 2. Instead of x, we're going to put 0 plus 4. Alrighty, and then just simplify. Plug in 0 for the x's and simplify. We're going to PEMDAS the right side of this function. -3 over 2 times 0 is just 0 plus 4, which is 4. Bam! That's the y-intercept of function a, which is g of x. Now we're going to switch gears and take a look at which one? Function b. Alright, we're now going to look for the y-intercept of function b. Alright, so y-intercept of b. b is the function f of x equals x plus 2 times x plus 6. Now this one, ladies and gentlemen, is a quadratic in factored or roots form. So to find the y-intercept, just simply set x to 0, exactly as we did with function a. Alrighty, so f of 0 means we replace the x's with 0, so we have 0 plus 2 multiplied by 0 plus 6. My 0 here looks like a 6. Let me fix that. Bam. Okay. Alright, so let's PEMDAS the right side of this function. Order of operations, do parentheses first. So 0 plus 2 is 2. 0 plus 6 is 6. And then multiply. 12. Are the y-intercepts the same for these two functions? The answer is no. Alright, so A and B do not, they do not have the same Y-intercepts. Okay, so the question is option 2 true or false? Option 2 says A and B have the same Y-intercept. That's false. Alright, let's keep going. Option 3. B and C has, B has a minimum and C has a maximum. Alright, so for option 3, it's looking at maximum and minimum here. So B has a minimum and C has a maximum. Now for these two, if you look at B and C, they're both quadratics. Okay? If you want to determine if a quadratic has a maximum or minimum, you look at the opening of the graph. Alright? Or you can think about it as the mood of the parabola. Is it a happy parabola or is it a sad parabola? So let's take a look at these two scenarios. So something that you want to remember. If you have a happy parabola, okay, what on earth is a happy parabola? A happy parabola is a case where your parabola looks something like this. Alright, so that's happy. It's like you're smiling. Alright, if you have a parabola that's happy or a parabola that opens up, the vertex is a low point, so you have a minimum. Alright, so when you're given a graph, if it opens up, it's a minimum. If you are given an algebraic equation, the a value has to be greater than 1. Alright, so when a is greater than 1, or you have a parabola opening up, your extrema is a minimum. Keep that in mind. Alright, so this is a happy case. How about sad parabola? Sad parabola looks like this. Bam. Something that opens down. Okay, so let's say there goes the eyes right there. Right? Okay, so you have a sad parabola. So if your parabola opens down like this, when given a graph just like C, you see it opens down, it's like a sad parabola right there, right? So if it opens down, in that case, you have a peak or a high point called a maximum. That's how you describe the extrema or the vertex of the parabola that opens down. Algebraically, if a is less than 1, or if the leading coefficient, when written in standard form, if the leading coefficient, it doesn't matter if it's written in standard form. If the leading coefficient is negative, it's going to be sad. Okay, if the leading coefficient is positive, then it's going to be happy. Alright, so let's go ahead and take a look at B and C. Let us start with B. For function B, let's see here. We have f of x equals x plus 2 times x plus 6. Now the question is, when you graph this parabola, is it going to be happy or sad? There are two ways you can do this. You can either graph it with your calculator and see what the opening is, or you can just think about what the sign of the leading coefficient is. The leading coefficient is the term with the biggest degree. So in this scenario, if you just multiply x and x, you will have the term with the biggest degree. X times x is x squared. It's positive, so it's going to be happy. Alright, so it's going to be opening up. So let's show the work so that everybody understands what's going on. So what we're going to do is we're going to expand this completely so you can see exactly what A is, and that will tell us the opening of the parabola. Alright, so we're going to FOIL this out. First outer, inner, last. So first outer, inner, and then last. Alright. Okay, so x times x, what do we have? X times x is x squared, and then outer 6x plus inner 2x plus 12. And then if we simplify, you have f of x equals x squared plus 8x plus 12. Okay, so what we care about here is the a value. The a value is the leading coefficient, which is positive 1. Alright, so since the a value is positive, since a is equal to 1, which is positive, guess what? This is happy, like positive people. Right? Positive people are happy most of the time. So this opens up because a is positive, which is 1. And what kind of extrema do we have here? What kind of extreme. It's a minimum. Okay, so this graph that opens up automatically tells us that B has a what? B has a minimum. Alrighty. Now how about C? Wow, C is easy, right? Why is it easy? Because they already gave you the graph and you can easily see what it is. C, what C is, it's sad, opening down. So if you're opening down, the extrema right here is a peak or a high point. How would you describe it? How would you describe a peak? A maximum or a minimum? You describe a peak as a maximum. Okay, so that's the description of the extrema for option C. We don't need to do any work for that one. So for C, what do we have? For C, it opens down because we are given the graph. It opens down. So since C opens down, the graph looks like that. That tells us that C has a high point known as the maximum. So C has a maximum. Alright, so B has a minimum, C has a maximum. Let's take a look at the options. It says B has a minimum, C has a maximum. Ladies and gentlemen, option 3 is the correct answer for question number 14. Alright, so let's take a look at option 4. We already know what the answer is, but let's take a look at option 4. It's very interesting here. So option 4, the first one says C has a maximum. We know that this is true because it's the same statement in 3. Okay, C opens down, so it has a maximum. But option A is kind of interesting. Option A is a linear function. Now this linear function, if you want to graph it, let's just graph it real quick. For option A, we have a y-intercept of positive 4, right? And then a slope of negative 3 over 2. So let's see what that looks like. I'm just going to graph it first and then we'll take a look at the statement. So we start with 4, 1, 2, 3, 4. That's your y-intercept. That is your b value. Okay, you begin with your b value. Okay, in y equals mx plus b. You begin with your b value and then you go down 3. 1, 2, 3 and over 1, 2. So that's your slope. Okay, if you don't understand what I'm doing right now, you don't have to panic because you have the luxury of graphing this with your graphing calculator. Although it's important to know how to graph for algebra 1, you want to know how to do this. It's important. Okay, so if you don't know how to do it, you have your calculator, you can just graph it. Now, what I wanted to stress is what is the minimum of this function right here? What is the minimum of a linear function that's decreasing? What does this arrow mean? This arrow means that this function decreases forever. So if this function decreases forever, what is the lowest value it will attain? The answer is none. It decreases forever, so it has no minimum value. So option A, function A, has no minimum. So even though this statement, C has a maximum, is true, this statement, A has a minimum, is false. So true and false is false. Okay, you can have part of a statement be true and the other part be false, and say that the combined truth value of the statement is true, is false. Alright, so the answer to option 4 is false, because part of it is false, so it makes the whole thing false. And we can clearly see that the answer to question number 14 is option number 3. Alright, let's take a look at question 15. It says, in this one we're taking a look at how to transform a word problem into an algebraic equation. It's kind of like a translation from word form into algebraic form. Okay, 15 reads, niece's sister is 7 years less than twice niece's age A. The sum of niece's age and her sister's age is 41. Question, which equation represents this relationship? So we have 4 options here. Alright, so let's start by declaring the variable that was already declared for us, which is what niece's age is. So let niece's age be let niece's age be A. Alright, so that's going to be the foundation for our equation. So let niece's age be equal to A. Alright? Now her sister's age is defined using niece's age. That's why I called it the foundation. So what is the sister's age? Niece's sister's age is described as being 7 years less than twice niece's age. Okay, so let's write that down. It's 7 years less than twice niece's age. Okay, and niece's age, we know what niece's age is, right? Okay, so 7 years less than twice. 7 stays at 7. Less than, what operation is less? Less means you subtract, okay? 7 years less than twice. What operation is twice? Twice means to double or multiply by 2, okay? And based on our declaration here, our definition, we have A as niece's age, so niece's age is A. Now, one thing you want to keep in mind is that when you are translating from verbal to algebraic form, you write it in the reverse order, okay? So 7 less than twice niece's age is not 7 minus 2a. You write it in the reverse order, okay? So you have twice niece's age, 2a less 7 minus 7, okay? So you want to be careful how you set it out. All right, so 7 years less than twice niece's age is 2a minus 7. Okay, we're told that the sum of niece's age and the sister's age is 41 based on the second statement. Niece's age and her sister's age has a sum. So let's write that down. The sum of niece and sister's age is 41. Okay, so niece's age is what? Niece's age is A. What does sum represent? Sum is the addition operation. So we're going to add niece's age plus the sister's age. What is the sister's age? 2a minus 7. Plug it right in here. So for sister's age is 2a minus 7, which is basically 7 years less than twice niece's age in verbal form, and that equals 41. Okay, so this is the algebraic equation that represents this statement provided for us here. So let's look at the options. Which one is the correct one? Oh, option A plus, see, this is a trick. They kind of switched it, so that's wrong. You don't want to do that. The correct answer to option 15 is option number 2. Okay, so this is how you transform word problems into algebraic equations. Thanks so much for taking the time to watch this presentation. I really appreciate it. Let us know what you think. If you found the contents of this tutorial helpful in your preparation for the upcoming Regents exam, let us know what you found easy to understand and what was complicated. Just post your comments in the comment section below. If you found the contents of this tutorial helpful in your preparation for the Regents exam, do give us a thumbs up. Your positive feedback is very valuable to us, and do share with your friends so that they can also benefit from this review material. Do not forget to subscribe to our channel for updates to the remainder of this review series. If you would like to gain access to the transcripts of this video, do visit our website at math.serve.com under New York Regents exam. Thanks again for watching and have a wonderful day. Goodbye.